Hello everyone, this is Mr. Molo for lesson 8-6, comparing linear, exponential, and quadratic functions. So for this lesson, we pretty much just need to say if the table or equation is linear, exponential, or quadratic. So let's go over what that means and what that looks like. So this first one is going to be a linear, y equals t. So nothing funny there. Just a normal like y equals mx plus b kind of a thing, except it's just y equals t. So they want us to put in these numbers for t. So if t equals 0, well then y equals 0, then 2. If t equals 0.2, then y equals 0.2. Same thing, 0.4, 0.6, 0.8, 1.0. So going back to, chapter, I think, 3, how do we tell if something's linear? Well, if they have a constant adding or subtracting pattern. So this one we have been finding for a while here. If we were asking if something's linear, it needs to have a constant adding or subtracting pattern. Okay, here we have y equals 2 raised to the t minus 1. So I'm going to show you how to put this in a calculator here. So I have 2 raised to the first number they wanted me to put in was 0 minus 1. That gives me 0. So I'm going to do 0, 0. I'm going to continue with 0.2. So 2 raised to the 0.2 minus 1. And we get 0.14. Actually, I'm going to round up to 0.15. And then we just keep going with that. So I'll just tell you the answers: 0.32, 0.52, 0.74, and 1. So if we see something like this, there's not really a pattern there, like 0.15, 0.32, 0.52, 0.74. There's not really a pattern there, and that's because this is an exponential. And I'll show you what a picture of an exponential graph looks like, but there's not really a pattern in an exponential graph. And then the last one here, you could probably guess, since the first one's linear and the middle one was exponential, this one's going to be quadratic. And we'll see in a second that there's actually a pattern here. So 0 squared is just 0. 0.2 squared is 0.04. 0.4 squared is 0.16. 0.6 squared is 0.36. 0.8 squared is 0.64. And then 1 squared is 1. So you see there's kind of a pattern here from 4 to 16 to 36 to 64. They're using all those perfect squares. If they had 3 in there, it'd be 0.9. If it had 0.5 in there, it'd be 0.25. So we kind of see a pattern here, and that's because quadratic graphs have a pattern. So hopefully it'll make more sense once we look at this picture. So you could graph all these and kind of see the pattern. That would kind of be the long way to do them all, is to graph and see what it looks like. Or if you can kind of just picture it, this needs to have a constant, if it's linear, constant adding or subtracting pattern. Exponential really isn't going to have a pattern. Numbers are just going to get bigger or smaller, depending on if they're going up or going down. And then here you'll see numbers are going to repeat because you're going to need one on the left side of the axis symmetry and one on the right side of the axis symmetry. Okay, so let's look at another one that have graphs here. Okay, so we can kind of look at the numbers and maybe get a good guess on what's going to happen here. But let's just graph a couple of these so we can kind of see one of each. So if I look at number 1 here, I'm going to graph -3, 2, -2, 4, -4, 4, -1, 8, and -5, 8. So somewhere up there. So as you can see, based on this graph here, it's a U-shaped graph. This is a quadratic. And then we can kind of look. I have numbers that are repeating. I have 4, 4, 8, 8. And then that 2 is my vertex, so it doesn't repeat. So there's one to the left of that 2 being my vertex. There's one to the right of the 2 being the vertex. So that's where we kind of get that, that U shape. All right, let's look at number 2. So I have -3, 1, 2, 3, 1, -2, 2, -1, 4, 0, 8, and 214. So it goes way off the graph. My 0, 8 is probably a little off there, but we can kind of see there is a curving pattern here. So this one would be exponential. And so as we kind of notice, from 1 to 2 to 4 to 8, almost a pattern there. You're kind of timesing by 2 there. 1 times 2 is 2, 2 times 4 is 8, 8 times 2 is, or 4 times 2 is 8, 8 times 2 is 16, not 14. So almost a multiplying pattern there, but then kind of gets that exponential curve. Now let's look at number 4. So I have 2, negative 4, 0, negative 2, negative 2, 0, negative 4, 2, and negative 6, 4. If we look at this, that looks like it's a straight line. That is linear. Another way we can tell is there's a pattern here. We're adding 2 each time. Negative 4 plus 2 is negative 2. Negative 2 plus 2 is 0. 0 plus 2 is 2. 2 plus 2 is 4. So we can kind of see the pattern there. So if you can see the pattern without having to graph it, great. Otherwise, kind of then the slow way to do these problems are to graph it. So let's see if we can see from the boxes here, from these tables, if we can see what the pattern is. So I'm looking here, I have 7 to 4 to 1 to negative 2 to negative 5. To me, it looks like that's going down 3. And when it goes up or down by constant adding or subtracting, that means it would be linear. Okay? Here I go from 6 to 2 to 0, back to 2, back to 6. I see some numbers repeating there. So I see 6 and 6, I see 2 and 2. 0, 0 must be my vertex. So that means it's quadratic. So the one that we were missing here was exponential, and that would have been if we kind of had that, non-pattern, close to a multiplying pattern, but not really. Okay? Here we need to tell whether it's linear, exponential, or quadratic, and then write the function. Okay, so now we need to write the rule. So first of all, let's figure out if it's linear, exponential, or quadratic. So here we have negative 4 to negative 1 to 2 to 5 to 8. Again, I see an adding pattern there. It looks like we are adding 3. So when we add 3, that's going to end up being our slope. So y equals 3x, and then we need our y-intercept, which is 2. So they're asking for our equation there. It's going to be y equals 3x plus 2, although it says it's a function, so then it should be f of x equals 3x plus 2. Okay. Number 8 here, I have negative 9 to 0 to 3 to 0 to negative 9. Again, we got some numbers that are repeating here. Negative 9, 0, 0. So I know this one's going to be a quadratic. And this one's a little tougher to figure out the equation. So first I need to figure out the intercepts. So if I figure out the intercepts, it's right there, negative 1 and 1. So x plus 1, x minus 1. And then we have to figure out what number is being multiplied on the outside there. And the way we're going to figure that out is we're going to use another point to help us there. So I'm just going to pick this negative 2, 9. You could have picked a 2, negative 9 or anything like that. So I'm going to set this equal as like a y equals and try to figure it out. So since I picked the point 9 or negative 2, 9, this is x, this is y. So I'm going to start it. Negative 9 equals, and normally we'd put like x here, but since there's already x there, so I'll put like a there. So we're trying to figure out what that a pattern is. So x I'd say is negative 2 plus 1, negative 2 minus 1. So we do some math here. So negative 2 plus 1 is negative 1. Negative 2 minus 1 is negative 3. So multiply those. I get negative 9 equals negative 1 times negative 3 is just positive 3a. Divide both sides by 3. Divide both sides by 3. We figure out that number in front should be a negative 3. So then this is going to be our final answer if they want us to write the equation there. And then this one, a ball is dropped from a height of 305 feet. The table shows the height and feet of the ball at t seconds after being dropped. Let the time t represent the independent variable. Tell whether the data can be linear, exponential, quadratic. Okay, so this one, like quadratic, wouldn't make any sense if you're dropping a ball, unless the ball happens to like bounce back up. Then it might make like that U shape on a graph, but probably not going to bounce all the way back up to the height that it went. Linear wouldn't make sense, like the ball's just not going to drop constantly at the same pattern. It's going to slowly gain speed. So this one would be exponential. So you've ever dropped something or you know how science works, when you drop something, it'll speed up until it hits its terminal velocity. And then once it hits its terminal velocity, it'll kind of level out. But, if they ask you what's going to fall faster, a golf ball or a bowling ball, and some people might think that they fall the same. Well, that's not going to be true because the bowling ball weighs more. So they both start falling at the same rate, but then that bowling ball is really going to pick up speed because it's heavier. So it'll fall kind of exponentially faster there.